Today we're going to talk about power and efficiency. So what is power? Well, it's the rate at which work is done. So anything that's a rate is going to be a quantity divided by time. And that's what power is. Power is going to be the work per unit time, or divided by time. Now, of course, work is equal to the change in energy, so you might see this written as change in energy divided by time. And of course, there's all different kinds of changes in energy. This could be a change in kinetic energy, a change in gravitational potential energy, a change in electrical energy, etc. Symbolically, we'd usually write P equals W over T, or P equals delta E all over T. And the units, well, it's going to be energy units, which is joules, divided by time units, which is seconds. And we have a special name for a joule per second. It's named after James Watt. It's called the watt. And we'll use a capital W to represent the watt. So let's try to get a sense for how big a watt, a joule per second, is. Here's a question for you. Pause the video, read it over, try it out, come back for the answer. In part A, we know that the apple has a weight of about 1 Newton. So if we're using a force of 1 Newton to lift it, we're going to have to lift it through 1 meter. So a joule is approximately the energy needed to lift an apple 1 meter. Part B, how quickly would we need to lift this apple to this height in order to work at a rate of 1 watt? Well, of course, 1 watt is equal to 1 joule per 1 second. In other words, we're going to have to take 1 second of time to lift our apple in order to do work at a rate of 1 watt. And then in part C, how many times per second would we need to lift the apple to this distance per second if we were to use the equivalent power of 100-watt light bulbs? Well, that would mean we'd have to lift our apple 100 times per second up 1 meter in order to be using energy at the same rate that a 100-watt light bulb does. So here we have a monkey doing push-ups. What I'd like you to do is to estimate how much power that monkey is using. So you're going to have to make some estimates as to what's the mass of the monkey and how high is he lifting his center of mass. So see if you can work out the power and then come back and see if your answer agrees with mine. So I estimated that the mass of the monkey was about 40 kilograms. And I think he's lifting up his center of mass there by maybe 30 centimeters or 0.3 meters. And the other thing I need to know is how much time it takes him to do 1 lift. And what I did is I figured out the time for 5 lifts, 5 push-ups. And that came out to be about 12 seconds. So the time for 1 lift, up and down really, would be equal to 12 divided by 5, or about 2.4 seconds per push-up. So now his power is going to be his change in energy over time. The change in energy, he's changing his gravitational potential energy. He is speeding up and slowing down, but his average speed would remain the same. So we're going to neglect any changes in kinetic energy. So gravitational potential energy would be given by mg delta h, and then the time would be the time for 1 lift. So he's a 40-kilogram monkey. We'll take g to be 10, since we're not going to be very precise here, and delta h was 0.3 meters per push-up, and the time per push-up was 2.4 seconds. If you work that out, you should get about 50 watts. So we've got a 50-watt monkey here. Here's an IB multiple choice question. Pause the video, try the question, come back for the answer. So the power should be equal to the rate of change of energy per unit time. I'll write that as a delta T instead of just a T this time. And the type of energy that we're changing is, of course, gravitational potential energy. We're not speeding up the water, we're just lifting it up with a constant force equal to the weight. So that would be the change in gravitational potential energy, the change in mgh per unit time. Now, of course, G and H are constants. They're not changing, so I can bring those outside the brackets. They're not changing, so I can bring them outside the delta. And that'll give me delta M, and the delta T I'll put right under the M. So this here, delta M over delta T, that's the rate that mass is lifted, which is what we're calling R. So our final answer here is GH times R, or R times GH. The correct answer is B. You may have heard the term kilowatt hour, and because it's got the word watt in there, you might think it's a power, but it's not really. A kilowatt hour, kilowatt dot hour, is the energy used by a 1,000 watt device. And a toaster would be about 1,000 watts. If used for 1 hour. So more generally, we said that power is equal to the change in energy over time. So that would mean your energy would equal power times time. So we're taking kilowatts, which is just 1,000 joules every second, and we're multiplying it by the time of 1 hour, or 3,600 seconds. Multiply that out, you get 3.6 million, and the units there are joules, energy units. So a kilowatt hour is 3.6 million joules. So in this course we're going to have 3 units for joules. If we've got really big amounts of energy, then we're going to use kilowatt hours. If we're talking medium amounts of energy, then we use the SI unit, the joule. And if we're using small amounts of energy, such as in atoms, we use what's called the electron volt. Turns out there's a simple expression for the power of objects moving with a constant velocity. But it's got to be a constant velocity. The expression turns out that the power will be equal to the force times the speed. And let's see how that comes about. If I do a free body diagram for this car, which we're going to assume is moving with constant velocity, then of course the vertical forces here are going to cancel out. Nothing interesting going on there, because there's no motion up or down. What's more interesting is the horizontal forces. And because it's moving at constant velocity, once again, these two forces have to be the same size. So we're going to have, say, a push force going forward and a resistive force pushing backwards. And those two will be the same size because it's moving with constant velocity. So now my power will be equal to the work per unit time. But of course the work is equal to the force times distance. Now the force we're talking about, well, it could be the push force or it could be the resistive force because they're the same size. The push force is the same size as the resistive force. So either one of them could be our force here. And then I can write this as force times distance over time, and hopefully you recognize distance over time is just speed. So we end up with power equal force times speed. Often in problems, an average value will be used for the force. So our car goes at constant velocity, but that doesn't mean our push force has to be constant. It always has to equal the resistance, but it could vary somewhat so as to keep the car moving with constant velocity. And then we could speak of an average push force being exerted and an average resistive force. So here we have an example of a train traveling at constant speed. See if you can work out the net resistive force acting on the train. So pause the video, try the question, come back for the answer. So because it is constant velocity, we can use power equals force times speed. That force, remember, it could either be the push force or the resistive force. In this case, it's going to be the resistive force that we're looking for. The speed we're traveling at is 50, and the power is 1 times 10 to the 6, or 1 megawatt. So our resistive force is going to be 1,000,000 divided by 50, or 20,000 newtons, which would be 20 kilonewtons. So the correct answer is C. Now when we're talking about devices like light bulbs, electric motors, we can talk about their efficiency. And the efficiency will equal the output power divided by the input power. Of course, the output power, that's the useful stuff. That's the stuff that you want. Whereas the input, that's what you got to give up. Now often you'll see the efficiency written in terms of work, and it would equal the output work divided by the input work. Now it's more correct to write it in terms of power, but usually we run our input for just as much time as our output, and as long as we do that, then we can write our efficiency as the output work over the input work. But it's really got to be over the same amount of time. This diagram up here, it's called a Sankey diagram. And the width over here on the left side would be proportional to the input power. So that represents 100% of the input power. Now if we've got a light bulb, what's useful to us is the light. And if it's an incandescent bulb, it actually only gives off about 5% of its input power as light. And the other 95% is kind of wasted as heat. So an incandescent bulb is much better at heating your home than it is at keeping it bright. So this Sankey diagram has not been drawn to scale, but if I'd drawn it to scale, I'd have 57 units. That is 95% of 60 would be 57 units to represent the width here for the heat power. And this width here would be only 3 out of 60 units wide, and that would represent the useful power, the light coming out. So our efficiency here would be equal to 3 divided by 60, or 5%. So here's an IB question on efficiency. Pause the video, try the question, and come back for the answer. So the efficiency of our motor here, it has an input power of 250 watts. So the input would go on the bottom, the output on the top. So we've got 250 watts as our input power, produces 200 watts of mechanical power. So that's the useful stuff, that's the good stuff that we want. And then 200 out of 250, that's 80%. So we've got 80% efficiency here. Here's another IB multiple choice question. Be careful with this one. Pause the video, try it out, come back for the answer. So our efficiency should be equal to that output power divided by the input power. Not much doubt about the input power. This width here represents the input power, and you can see that that's 8 grids wide. So I'm going to put an 8 in there for the input power. Now for the output power, no doubt we've got to include this. This is lifting up the load. That's definitely useful power. And we definitely don't want to include these 2 units because we know that those are losses. But what we've got to be careful of is they're asking for the efficiency of the motor. They're not asking for the efficiency of the system. So we should include these extra 2 units here in the efficiency of the motor, because in regards to the motor, that is useful energy, is just being eaten up by the pulley. So in total we get 6 units of useful output for the motor. And our efficiency is, of course, 75%. Now we don't usually think of an incline as being a machine, but it is a machine, and we can talk about the efficiency of an incline. So let's try these questions here. How much work will it take to push the 2 kilogram block up the frictionless incline? Well, that means we're going to push it to a distance of 6 meters. And if there's no friction, the force that we're going to have to use is going to equal to the component of weight acting along the incline. And if this angle here is theta, then this would be mg times the sine of theta. Now, of course, the sine of theta is the opposite over the hypotenuse, so this is going to be mg times 3 all over 6. So if we push the block with a force of mg times 3 over 6, our force will exactly balance out that component of the weight, and we'll push it up at constant velocity. And the work done would be equal to that force times the distance we're pushing it through. In other words, it's going to be mg times 3 over 6 times the distance, which was 6 meters. So we're going to get 3 times mg, m was 2, we're taking g to just be 10, so we're going to get a grand total of 20 times 3, or 60 joules, to push the block up the ramp. Now, if we had just lifted the block straight up, the work would be equal to, well, force times distance again, but we'd only have to lift it up by 3 meters this time. But we'd have to use a force equal to the full weight of the block, the full mg, to push it up with constant velocity. So we'd end up with 2 for the mass, 10 for g, and 3 for the distance that we're pushing it up through. So once again, we get 60 joules of work. So it takes what we would expect. If there's no friction, it takes the same amount of work to push it up the incline as it does to lift it straight up. So what's the efficiency of the frictionless ramp? Well, the efficiency would equal the power out divided by the power in. Assuming we do those in the same amount of time, that would be equal to the work output divided by the work input, which would be 60 joules is the output. The output of our machine is simply the ability to lift up the block straight up. That's what we really want out of our machine. We want to get the block higher. The input is what we've got to do ourselves, and that's to push it along the incline. So we get an efficiency there of 60 joules over 60 joules, or 1, meaning 100% efficiency. So now let's take a look at the efficiency if we add some friction. So our input work would be the amount of work done to move it along the incline. So we're going to have to use a force equal to that mg times 3 over 6. That's the component of the weight along the incline, mg sine theta. Plus, we've got to add on an extra 10 newtons of frictional force. And once again, we have to push it through 6 meters. So we're going to get an input there of 2 kilograms times 10 newtons per kilograms times 1/2 plus another 10 due to friction. Multiply that by 6 and we'll get 120 joules of input work needed to push it along the incline. In other words, since the frictional force was equal to the component of weight along the incline, we doubled the force that we had to use, and it took twice as much work. So what's our efficiency now? That should be the output work divided by the input work. And the output work doesn't change. It's still, the output is still just lifting the mass straight up. That still takes 60 joules. But what's different now is we're going to have to put 120 joules into pushing the block up the incline with friction. So we're going to get 0.5 or 50% efficiency because of friction. Just like inclines, pulleys have this great advantage in that you can use a force much smaller than the weight of the object to lift up that object. So let's take kind of an ideal case here, and we'll imagine that we've got frictionless, massless pulleys. And what that'll mean is that the tension is the same throughout the rope. And you'll notice here that this weight here, it's being lifted by two strands. And both strands have that tension T in them. And then the tension here is exactly the same. In other words, this pull that the person's going to pull with is going to equal the tension, at least if he lifts it with constant velocity. So if we consider the input side, then the work would equal force times distance, and the force that's going to have to be pulled with would be the tension. And they're going to have to pull over some distance here, which I'm going to just call D. Now let's consider the output. For the output, that's just lifting this mass up. And you'll notice that there's not just one strand pulling up the weight, there's actually two strands pulling up the weight. So you've got two of these tension forces lifting up the weight. So for our output work, the force is going to equal 2T, one for each strand. And you're going to lift it up some distance h. Let's call this the distance h here. Now if we've got 100% efficiency, then the input work and the output work should be the same. In other words, T times D must equal 2T times h. We can cancel out the T's and we get that D is equal to 2 times h. In other words, sure, we get to use a smaller force, T compared to 2T, but we've got to pull through twice the distance as we lift the object. So we get to use half as much force, but we got to pull through twice the distance. Let's summarize the big ideas from the video. The first was that power was the rate at which work is done, or the rate at which energy is transferred. So we had this equation that power is equal to W over T, or change in energy over T. And the units would be the watts, which is equal to a joule per second. We saw that in the case that we had something moving with a constant velocity, that we could write the power as equal to the force times the speed. We saw that kilowatt-hours were big units of energy. So the hydro to your house is generally measured in kilowatt-hours. And 1 kilowatt-hour would be approximately the amount of energy needed to run a toaster for an hour. We saw that efficiency was equal to the ratio of the output power divided by the input power, or we could write that in terms of work, the output work divided by the input work. This output work here, it's the useful stuff that you're after, that you want. The input is what you got to give up to get it. And then we looked at inclined planes, and we saw that the input work on an inclined plane would be equal to the force you got to push with times the distance up the incline. And the output was simply lifting the object straight up to its height. So the output work would be mgh, where h here is the height of the incline. And the last thing we looked at was pulleys. And we looked at a simple pulley system. And we just considered a 100% efficient pulley system where there was no friction and the pulleys were massless. So this would be 100% efficient. Our input, the input work, would be equal to the tension in the string times whatever distance you got to pull that rope through. And in the ideal case, that would be equal to the output work, which would be equal to 2 times the tension, because we got 2 strands lifting up the rope here, times the height that you lift your weight. And as we saw, the height would be only half as big as the distance that you got to pull through. So you get to use half as much force, but you got to pull through twice the distance. And that's all for today, folks. Thank you very much.